So in this example, we're given the simple circuit shown here, and we're asked to find the value of V, so that's the voltage at this node here. But when we look at this network, we have a little bit of a challenge in that they have this dependent voltage source in between the two nodes that we would use for nodal analysis. So this can be a little bit tricky. So what we do here is we're going to utilize a technique which is called a supernode. And so that means that if we're going to declare a supernode, we're going to take this part of the circuit and declare that as one node. Now you can see there's actually two nodes inside of there, but that's why we call this a supernode. So we're going to consider that as just one node. So if we do that, let's see if we can develop some equations for that with all the current entering and leaving the node. So when we look at that, the first thing we'll look at is this branch here. And when we do that, we'll see that that's just going to be V1 over minus 24, V1 minus 24 over 4. And then we will come down to this node, and we can characterize that then as V1 over 4. And then finally, we're going to look at this one, and that's going to be V over 4. Now we note that we still have this resistor here, but we can see that it's actually going in and leaving our supernode, our single node. So therefore, in theory, there should be no current there. Of course, there will be current, but we don't really care about it at this point because it doesn't really affect what we're trying to calculate. So that being the case, then we've looked at all the branches entering and leaving our supernode, and so we can set that equal to 0. So now we need to take a look at what's going on inside our supernode, and that involves this dependent voltage source right here. And so we can write then that the difference between our two nodes inside of our supernode, so that'll be V1 minus V, that's going to be equal to the value of this dependent source, which it's defined as 2IX. So let me write that a little later, 2IX. However, we see here that IX is defined as the current through that branch. So we can write that then, IX is just equal to V over 4, Ohm's law. So now we can take that and substitute that into here. When we do, it's V1 minus V is equal to 2 times V over 4. And then that means we can multiply that out and rewrite that. And when we do, we come up with V1 is equal to 1.5 V. All right, so now if we want to take this relationship, and everywhere we see V1, which is here and here, we want to replace that. So if we do that replacement, then we will have 1.5 V minus 24 over 4 plus 1.5 V over 4 plus V over 4 is all equal to 0. And so now we see we have one equation, one unknown. We can multiply through by 4, and that'll give us 1.5 V minus 24 plus 1.5 V plus V is equal to 0. And so that gives us, add up the V's, that's 1.5, 1.5 is 3, plus another is 4, so that's 4V. Move the minus 24 to the other side by adding 24, so we get 24. So finally we get V is equal to 6 volts. So that's the answer to this example. So one thing that's interesting is these 4 ohm resistors could have been any value as long as they were all the same. They made no difference to the voltage at that node. So anyway, just an interesting fact. But the main point is the answer to the problem is the voltage at node V is 6 volts.